Okay, so we're going to be talking about how to create a graphical model, most importantly, displacement time graphs. Have you guys done displacement time graphs in physics? Oh, so most of you guys take physics. Okay, so then this should be a review for you guys, unless advanced functions is teaching it wrong. So for problems involving motion, a possible graph shows displacement, distance, height, or depth versus time. So time is always the independent variable. So this is obviously the x-axis. And displacement is always the dependent variable. So this is on the y-axis. So speed is the slope or rate of change of displacement with respect to time. Speed is equal to the absolute value of the change in displacement over the change of time. So can speed be negative, or does it always have to be positive? It has to always be positive. The sign just tells you where you're going. Okay, so if the speed is positive, that means you're going away from your point of reference. If you get a negative absolute value, that means you're going back towards your point of reference. Okay, so I'm going to show that to you later on. So the magnitude of the slope of the secant line represents the average on the average speed on the corresponding interval. The magnitude of the slope of the tangent line represents the instantaneous speed at a specific point. So to gain insight into how speed changes over time, one must observe how the slope of the tangent lines change at different points on a graph. So when we have an increasing line, the displacement increases as time increases, which means the velocity is positive, which means your velocity keeps on increasing. If we have a decreasing line, that means your displacement decreases as time increases, which means your velocity is getting slower. And if you have a horizontal line, that means your speed is automatically 0 because you're not moving at all. So there's no rate of change or instantaneous rate of change at that point in time. So you guys probably are reminded of this type of question when you guys were in grade 9, making a distance time graph. So Serena runs a 1 kilometer each day as part of her daily exercise. From home, she first runs 200 meters at a constant rate for 2 minutes, then jogs another 300 meters at a slower pace for 6 minutes. And after a 2-minute rest, she races back home in 4 minutes. So we're just going to label our graph. So we have 2, 4, 6, 8, 10, 12, 14, 100, 200, 300, 400, 500, and 600. So the first piece of information we have is for the first 2 minutes, she runs 200 meters at a constant rate. So that's 200 meters at a constant rate. So there's 2 types of graph. There's displacement time or distance versus time graphs. In a distance versus time, if your slope is flat, then you are not moving at all. But I think in a velocity time graph, if it's a horizontal line, that means your velocity is constant, I believe. I don't know if I'm wrong or not. Or the speed is constant at that point. So our next segment, she goes for 300 meters, and this takes her 6 minutes. So from 2, we end up at 8. So she goes another 300 meters for 6 minutes, so we get up to 500 meters. And then she takes a 2-minute rest. So from 8 minutes to 10 minutes, she is resting for 2 minutes. And then she races back home in 4 minutes. So now that we drew our distance versus time graph, now we need to answer the following questions. So B is asking us, what is the average rate of change in her distance in the first 2 minutes? So the average rate of change is given by delta D over delta T. The distance she ran in the first 2 minutes was 200, and this was over a 2-minute time period. So our average rate of change in the first 2 minutes is 100 meters per minute. C is asking us, what is the average rate of change in her distance in the next 6 minutes? So in 6 minutes, after the 2 minutes, she ran 300. So now we're looking at the time interval of T is greater than or equal to 8, or greater than or equal to 2, but less than or equal to 8. So again, delta D over delta T, she ran 300 meters from 2 minutes to 8 minutes, and it took her 6 minutes, which means her average rate of change was 50 meters per minute. So C is asking us, what is the instantaneous rate of change at 6 minutes, 9 minutes, and 12 minutes? So just by looking at the graph, what was her instantaneous rate of change at 6 minutes? So which segment of her run does 6 minutes fall under? So 6 minutes falls in between the 2 to 8 minute interval. Okay, 6 minutes is right over here. So what did we say the rate of change between 2 minutes and 6 minutes was, based off our answer from C? Right, 50 meters per minute, which means her instantaneous rate of change at 6 minutes is 50 meters per minute as well, because the line in our distance time graph is a positive straight line going up. So there's no real secant or tangents to find. So the instantaneous rate of change at 6 minutes is 50 meters per minute. Okay. What do you think the instantaneous rate of change would be at 9 minutes? it would be 0 meters per minute. And last but not least, can somebody tell me the instantaneous rate of change at 12 minutes? Remember, you're just taking the slope of that last line segment. Yep, thank you, Jose. It would be 125 meters per minute because she ran 500 meters back in 4 minutes. So 500 divided by 4 gives us 125. So now what we're going to do with the information in question D, we are going to draw a speed versus time graph for Serena's run. So in the first 2 minutes, so we're going to label again, 2, 4, 6, 8, 10, 12, 14. And our speed, 25, 50, 75, 100, 125, 150. So for the first 2 minutes, she had a speed of 100 meters per minute, okay? So for the first 2 minutes, she went at 100 meters per minute. From minutes 2 to 8, she had an average speed of 50 meters per minute. From minute 8 to 10, she had an average speed of 0 meters per minute, so she didn't move. And last but not least, from 10 minutes to 14 minutes, she had an average speed of 125 meters per minute. So that is what your speed versus time graph would look like for this example. Okay, so when the speed is variable, one of the 4 scenarios may occur. So an increasing curve indicates that the displacement increases as time increases. So when time increases, here we see our displacement is increasing, which means that the speed is increasing as time increases, which means that the slope of the tangent each time gets steeper. And then the next one we have as time increases, the speed or the displacement kind of levels off. So speed is decreasing as the time increases. This just means that the slope of the tangents are decreasing as we keep going farther into the x-axis. And then it's the same idea when a decreasing curve indicates that displacement decreases as time increases. So here we have the speed is decreasing as time increases for the first example, which means that the slope of the tangents are steeper or are decreasing. Tangent, 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 tangent. So at one point they will have a instantaneous rate of change of close to 0 or at 0. And then for the next one, we have the speed is increasing as the time increases. So even though it's a curve going down, the tangents still keep getting bigger and bigger. Okay? We have 2 more examples and then you guys are done. So a flask, a beaker, and a graduated cylinder are being filled with water. The rate at which the water flows from the tap is the same when filling all 3 containers. Draw a possible water level versus time graph for these 3 containers. Okay, so for the first one, a graduated cylinder, we're going to have a constant rate of change. So as time increases, the height is going to increase. Okay? And for the beaker, because it's smaller than the graduated cylinder and it has a wider base, the level of water won't fill as quickly as the graduated cylinder. So as the beaker is being filled with water, it will have a less steeper slope than the graduated cylinder because it has a wider base and it is shorter than the graduated cylinder. In terms of volume, they might not be the same, but at the end of the day, the beaker will take longer to fill because of the width of the base. And who can tell me what the flask might look like, or what shape would it look like? It would be an increasing curve, okay? So here's the base takes forever to fill, and because as we get higher up the flask, the more narrow it gets, so the more quicker it'll fill up towards the top. And then we're going to do our last example. So example 3 is the speed versus time graph where a moving object is shown. How far did the object travel from 0 seconds to 8 seconds in meters? So we have our lovely triangle, which you guys probably do a lot in science. Distance is speed divided is speed. Speed is distance over time. Time is distance over speed, and distance is speed times time. So in order to find the amount traveled, what are we going to do with each line segment? So we have segment 1, segment 2, segment 3. So we're going to multiply the speed and the time. So for the first 3 minutes, they had a speed of 2 meters per second. Sorry, this should be seconds. So 2 meters per second, and they took 3 minutes, which means they went a distance of 5 minutes. For segment 2, their speed was 3, and the time they spent was another 3 minutes. So you get 9 meters. Sorry, 3 times 2 is 6. I made a mistake. And then the last segment is distance is equal to, they had a speed of 5 and did this for 2 minutes, which is equal to 10 minutes. So why don't we count the last little line over here? Why does from 8 and onwards not count? No, but look at the restriction. Because it says from 0 to 8. So 8 and beyond does not count. So now that we need to find our total distance, all we're going to do is add up the first 3 segments. So total is equal to 6 plus 9 plus 10, which is equal to 25 meters. Therefore, the object traveled 25 meters from 0 to 8 seconds. Okay, so that's pretty much it for today. I think we have one more lesson left, and that I'm going to do tomorrow. So other than that, you have no more assessments. I'll try to give you guys your final mark by tomorrow. What else? Also, since I'm going to be recording the lesson tomorrow, I guess I won't be on the call with you guys tomorrow. But it's been a great quadmester, to say the least. You guys are pretty good, handed in stuff on time. You guys haven't been a pain in the butt with handing things late, unlike my night school class.